we are happy to have John Harnad as a speaker today from Montreal. And the title of his talk is Bilinear Extensions of Lattices of Kp Tau Functions and Bkp Tau Functions, Determinantal and Pfaffian Representation.
Okay, so thanks very much, Sasha. I'd like to thank Alexander for the kind invitation to speak at your seminar. And it's a great pleasure. At 13 hours discrepancy and maybe the opposite pole of the world, we can still communicate. So here's the title. It's about Kp and Bkp tau functions, in fact, lattices of such things. I'll explain what I mean by that. And also representing these in a determinantal and Pfaffian way. So this is partly based on joint work with Ferenc Balog, with Jacques Urtubise, and Sasha Orlov. So I'm not sure who in the audience is familiar with the notion of tau functions, but I think that you've probably seen them before. In any case, I just want to remind you, well, here's an outline of the talk. I will first just say what I mean by Kp and Bkp tau functions, and then I'll do a little bit of a review of some tools which are necessary when talking about them, partitions, Schur functions, and so on. And I will speak about an identity which is really just a matrix identity, but has some deeper meaning, relating minor determinants to Pfaffians of skew matrices. Then I will give the Fermionic representation of Kp, Bkp, and Bkp tau functions, which is the basis of the main result, because I'm going to take this determinantal identity and turn it into a very general result relating lattices of Kp and Bkp tau functions. And then I'll speak about expansions of one in terms of the other and go over some examples, and also, if there's time, give you some specific determinantal and Pfaffian representations that generalize the old representations that apply to Schur functions. So first of all, I have to say what these things are. So before looking at the formalism, I just want to recall that tau functions are a tool that were introduced, very central tool that were introduced to the theory of integrable systems, well, originally by Hirota, but it was really developed geometrically and in full beauty by Sato. And they have multiple roles. I'm not going to talk about the applications. I'm only going to talk about properties. But the applications of tau functions include a vast array of domains of mathematics and physics. I'll just list a few of these. Tau functions appear. Originally, they appeared as sort of in the sense of dynamical systems, or actually completely integrable dynamical systems where you have many or an infinite number of commuting flows. They appeared as generating functions for solutions of such integrable hierarchies, and that was the original setting. But in fact, already from the beginning, there was a sort of quantum field theoretical interpretation that was in the works of Sato and his school. And they also play an equally important role in statistical mechanics and in quantum spin chains and other integral quantum systems, or integrable lattice models, where they appear in the role of partition functions, characterizing either a many-body system or a statistical system. Another role that since about 30 years we know exists is that they appear as generating functions in the sense of combinatorics. That is, you can expand them, and the coefficients in expansion have specific applications in a variety of domains, but especially in enumerative geometry, and especially in relation to the moduli spaces of Riemann surfaces. So that was quite a spectacular, I think the first appearance of that was with the Kontsevich-Witten integral, but this has been greatly developed since then. In some sense, Schur functions as generating functions for something combinatorial or group theoretic really goes back quite a long way, because the Schur functions, which I'm going to talk about, which are actually special cases of tau functions, can be thought of as generating functions for characters of the symmetric group, if they're developed in terms of the power sum symmetric functions. The coefficients are exactly the characters of symmetric groups. So that was a very old application before it was known that the Schur function is a tau function. Another guise in which Schur functions appear, which is very much related to integrable systems, is all higher genus Riemann theta functions are special cases of Kp tau functions. More specifically, it's not really the theta functions, the so-called Klein sigma function, which is a slight variant in which you, well, I won't go into that, but basically higher genus theta functions or sigma functions are also Kp tau functions. I mentioned the Schur functions. I'm distinguishing two different types of hierarchies, BKP, Kp. In some sense, Kp is related to the general linear group in infinite dimensions, and the Bkp is related to the orthogonal group in infinite dimensions, and they have an intimate relation between them, and later on I'll be discussing that. But other special cases of tau functions, which play a very big role, it's related to their role as partition functions, but matrix integral partition functions are very often in families of measures suitably defined. Under perturbations, there are variations and there are deformations, and these are also Kp or Bkp tau functions. Many of the well-known matrix integrals, including very old ones which appeared in representation theory, such as the Itzigson-Zubair integral, has an interpretation as the evaluation at power sums, at trace invariance of the Itzigson-Zubair integral. So many applications in a variety of domains. So now I'm going to go on and just speak about what is meant by a Kp and a Bkp tau function. But remember that special cases of these are the things that I just mentioned, the Schur functions, which are characters for the general linear group and very fundamental in the theory of symmetric functions, Riemann theta functions, matrix integrals. Oh yes, I forgot, hypergeometric functions. Hypergeometric functions, either of scalar or of matrix arguments, are also special cases of Kp. So a wide variety of functions that appear in mathematics and mathematical physics. Okay, so here's the definition. This is according to, well, it goes back quite a long way, but it's according to the approach of Siegel and Wilson and of Sato. So a Kp tau function is a function of an infinite sequence of parameters, real or complex, which we think of as mutually commuting flow parameters, T1, T2, T3. So there is some abelian group that is acting on some phase space underneath it. And what characterizes this class of functions can be programmed into one single equation. And this is called the Hirota bilinear residual relation, which actually includes, when you look at it, because of the parameters that are arbitrary, it includes an infinite number of partial differential equations, of which the most famous is the so-called Kadomtsev-Petviashvili equation, which is this one. I'll explain in a moment how you get that out of the tau function. But what characterizes the tau function is the fact that it satisfies this formal residue equation, which, when I say formal residue, I mean we think of all of the quantities, all of the functions that appear as actual formal series, Laurent series in a variable z, and the residue it could be thought of as 0 or infinity, is the coefficient of the 1 over z term. That's what is meant. It can, in certain cases, actually be thought of as a contour integral around the origin, around infinity. But in general, formally, it is always a residue, that is a 1 over z term in a formal Laurent expansion. So the rule is the following. We put in the independent variables, the flow variables t, and two values. So t and t minus delta t, where delta t is anything, any infinite sequence of perturbations of the t value. And we also subtract and add a certain infinite sequence of numbers determined by the z, which are given by this notation. Z inverse bracket means the sequence 1 over z, 1 over 2z squared, etc., etc. We subtract that from the first term, we add it to the second term, we multiply the whole thing by an exponential of an infinite series in z with the coefficients, the delta t's. And we take this and expand it and equate the 1 over z coefficients in the expansion to 0. Now, there's a subtlety here because they're both positive and negative infinite powers, I mean, an infinite sequence of powers. So what does it mean to multiply such things? Well, if you look carefully, what this is an equation that must be identically satisfied in delta t. And if you take it each delta t to any power or coefficient, there are only finite sums. So you do not have an infinite, you never have a situation where you have to multiply together two infinite formal Laurent series. There's always only a polynomial part. And so this is a well-defined equation when you look at it as identically satisfied in the deltas. And it implies an infinite number of partial differential equations for the tau function, which are very often expressed in terms of something derived from the tau function. So that's why the tau function, in the sense of general dynamical systems, is a generating function. So if you take the second partial logarithmic derivative of the tau function, you equate the first flow variable to x, the second to y, and the third to t, and forget the others. Those are just spectators. Take the second partial derivative of the log, it follows in particular one of the infinite number of equations that this implies is this Cadon-Seth-Petriashvili equation. In a sense, they could all be viewed as equations which involve evolution in some time variable. T here is this third flow variable, and partial derivatives in two other variables. In this case, it's T1 and T2, but every combination appears. Okay, so I'm not going to go into the theory behind this, but I've already mentioned that it's got multitudinous applications. So we're going to be looking at functions which satisfy such equations. And now there's a variant on this, which is very, very similar. So the next slide shows that, and that's called the Bkp Tau function. So the Bkp Tau function similarly is a function of an infinite sequence of variables, only in comparison with Kp, it's better to think only of the odd flow variables, T1, T3, T5, etc. And again, you have a formal residue equation that looks a little bit different. There's a dz over z, and there's a right-hand side, but it's again a bilinear equation. Again, one has this notation. In the Bkp case, we only have the odd powers appearing. So only odd variables appear in the t's and in the z brackets. So this is identically satisfied, and the delta t variables again, which again are infinite odd sequence. And that gives you another hierarchy, which is different from but related to the Kp hierarchy. And I'm writing in a different notation here. Very often these bilinear equations, the previous one that I wrote was in terms of the second logarithmic derivative. This is in terms of the tau function itself. The two are equivalent. I mean, there's a similar way that I could write the Hirota equation, this equation in terms of a bilinear expression in taus, and similarly for the Bkp. These are the a very standard operator is used in the theory of integrable systems introduced by Sato. They're essentially biderivatives. So this is a function acting on a product of two copies of the tau function. That's why it's bilinear, in such a way that the D1 or D2 or whatever is always a sort of biderivative, in the sense that you increment, in the first one, you increment the t variable by a plus delta t, and in the second one by minus delta t, divide by delta t and take the limits. So that's what these Sato derivatives mean. And okay, so this is a constant coefficient bilinear partial differential equation for t, for tau, in which the coefficients are all constants, but the derivatives are all with respect to the flow parameters. So here's the first equation of this infinite BKP hierarchy. Now, I mentioned earlier on that the Schur functions, and there's an analog of Schur functions, the so-called Schur Q functions, which has a similar properties, are the building blocks out of which all Kp and Bkp tau functions are built. So in particular, I'll define them in a second, but the Schur function can be either thought of as a group character for the GLN group, if we properly interpret the t variables, or as just one of the standard bases for the algebra of symmetric functions. And the Q is similarly so, but it only involves odd powers as symmetric functions. And so, in fact, it generates a smaller ring, a smaller algebra. So how are they defined? Well, first of all, we take what are usually the independent variables in symmetric polynomials or symmetric functions, call those x's. So there could be a finite number. Here I've written it as an infinite number, and form the power sums out of these x's. That's a symmetric function. You normalize it with a 1 over j, and you call that tj. And as is well known for anyone who's familiar with symmetric functions, one can equally well use the tj's as a generating basis for the ring of symmetric functions. And so we can just replace any symmetric function by a function of the power sums. And that's what we do. So we think of the Schur function not as a function of these x variables where it's a symmetric function, but as actually a polynomial for every lambda. I have to explain what lambda is. That's a partition. I'll do that in a moment. But for every lambda, this is a polynomial, a graded homogeneous polynomials in the t variables, which play the role of flow variables for Kp. But these should be viewed as the power sums, normalized power sums. Similarly for Q, the Q Schur functions, the lambda and alpha I will explain in a moment, but I'll just say for those who know the words, lambda is just an integer partition, so it's a weakly decreasing sequence of non-negative integers, and alpha is a strict partition, so that's a strictly decreasing sequence of integers, positive integers. So that's what labels the S and the Q, and the independent variables are just like in the Kp and Bkp. Well, these are particular solutions. Every Q alpha is a solution of the Bkp hierarchy, and every S lambda is a tau function of the Kp hierarchy. Okay, so let's just, these are the building blocks in the sense that every,
John, excuse me, question?
Yeah.
So there are different versions of BKP hierarchy.
Sorry?
Small BKP. There are different versions of BKP. Small BKP, big BKP. And so
yes,
you're working with.
Yeah. Okay. This is the small BKP. This is the original one introduced by Date, Jimbo, Miwa, and Kashiwa. Yes, there's also a big KP, and I'm not talking about that today.
Okay. Thank you.
So maybe because that's a specialized question, I should say something for the other members of the audience. What is meant by the small and the big is the phase space on which these are acting. In a sense, the small is contained, the BKP is contained inside the phase space for the KP. Whereas for the big KP, it's the opposite way around. The big KP contains the KP phase space. It's just the question of how you construct the underlying groups as infinite groups. Okay, so so we have this. Now let's remind everyone what a partition is. So a partition is a weakly decreasing sequence of non-negative integers, which eventually saturates at 0. So you can add as many zeros at the end of this sequence as you like, and it's convenient to do that. The length of the partition is the number of non-zero elements, and the weight is the sum of the elements. So we say that if the weight is this, n, then lambda is a partition of n. It can be represented as is well known by Young diagrams, which are rows of boxes. The number of squares is the parts of the partition. The parts are the lambda 1, lambda 2, etc. So here we have 4 for lambda 1 and 2 for lambda 2 and 1 for lambda 3. And eventually it's all filled with zeros, so you don't need to show the other ones. So L of lambda is the number of rows of boxes, and lambda I is the number of boxes, the number of squares in the ith row. An equivalent notation, which is very important, is the one introduced by Frobenius, completely equivalent. Instead of saying what the number of boxes, number of squares in each row is, you say what the, along the diagonals, you say how many there are to the right and how many there are below. These are called the arms and the legs. So A1, B1 are the arm and leg, first arm and leg length. You go to the second diagonal, A2, B2, and so on. And the number of diagonals R is called the Frobenius rank. So that's just a completely equivalent. You can always translate one into the other, but they're both useful. So here's a formula. There are many formulae that are equivalent for defining Schur functions, but the oldest one goes back either to Jacobi or Cauchy. Cauchy already had these things, and Jacobi studied them and had derived many properties. So this is called the bi-alternant formula. An alternant is a special determinant, which is formed by evaluating a sequence of functions on different values. So this is here it's the power functions, where the powers are given essentially by shift of the parts of the partition. And it's a ratio. They're both determinants. This is the van der Moom determinant. And so actually it's really, if there's a finite number of x's, as I have here, only n, finite number of x's, this is a polynomial in the x's. It's a polynomial of degree equal to the weight of the partition. The reason being that the zeros in the denominator occur exactly when two rows are equal. So xi equals xj, then the van der Moom determinant vanishes. And also the numerators, so they cancel. So the denominator polynomial exactly divides the numerator polynomial, leaving a polynomial, and that is the Schur function. So that's one way to define it. There are many others. So in this way, these are homogeneous symmetric polynomials, and the xi's of degree equal to the weight. And now I'm going to define the Q Schur functions. I could define them with a similar formula. I'm just choosing not to do it. This is a determinant. The important thing to distinguish the Schur functions from the Q Schur function is that whereas Schur functions are determinants, all the formulae for the Schur functions are determinants of something. The Q Schur function is a Pfaffian. So a Pfaffian is only defined for skew symmetric matrices, and it's so it's well known. I'm not going to define it, but it's a very well known object, which I will give a Pfaffian formula to define the Q Schur functions, which is not the exact analog of this. So there are other formulas called the Jacobi-Trudi formula and the Jambelli formula, all determinants. And I'm giving the analog of the Jacobi-Trudi formula, which was the original formula that Schur used to define these things. So how do you do it? You do it by first defining elementary Q Schur functions. They have one index. They're indexed by the non-negative integers. And this is the generating function for them. So you expand this as a series in Z, and the coefficient of the Z to the J power is the definition of Qj of TB. Only the odd elements come in because of the cancellations between the numerator and the denominator. So only odd terms come into the expansion. And if you look carefully at the definition of the square Z symbols, you'll see that these two things are the same. That really is so these are really the power sums in the x's. Okay, so these are the elementary Q-Schur functions. Now we define some bilinear expressions in these, Qi, Qj, plus a certain finite sum over Qi plus k and Qj minus k. Define this matrix and note n0 if ij are equal, and it's a fact that follows from this formula that this expression, if the i's and j's are interchanged, goes to its negative. So it's a skew matrix. So it's skew matrix, you can take Pfaffian, and you do, that's what Schur does. You take a sequence, they have to all be distinct, of coefficients, non-negative integers, and define strict partition using these, their decreasing sequence, and take the matrix. Of course, this could be either one could be larger or smaller. It's a skew matrix, and you can take the Pfaffian of that matrix. Now, only if it's of even order does that make any even cardinality does that make any sense. But you can define Q alpha for odd cardinality strict partitions as well by simply, by definition, adding a 0 at the end. If you have already a 0, that just gives nothing because it's anti-symmetric, so it vanishes. But if there's no 0 in the original alpha and R happens to be odd, then the rule is add a 0, comma 0. So you add a 0 element, and that makes it into an even dimensional matrix. You can take that Pfaffian as well. So that's the Schur original definition of the Pfaffian of the Schur Q functions. They, by the way, they both have group theoretical meanings. I don't want to go into that, but this can also be thought of as the group, as the character of a representation of the general linear group in which the x's are the eigenvalues. And the lambda denotes the type of tensor. So you take all tensor representations of mixed tensors of all symmetry, and those are labeled also by partitions. As everyone knows, the rows of the Young diagram are the symmetry. You do this Young symmetrization using lambda. Anyway, for those who are not representation theorists, this is not interesting, but you should know that that's one role that the Schur functions play. And similarly, the Schur Q functions also are generators of projective representations, but I don't need that property, so I'm not going to go into it. Now, the main result for our purposes is this. Every Kp Tau function can be written as a linear combination, infinite in general, of Schur functions with coefficients that have a special meaning, call them pi lambda. And similarly, every Bkp Tau function can be written as a linear combination of Q Schur functions with coefficients that have a special meaning. And what the meaning of this is, the Hirota bilinear relations that we wrote down for tau Kp and tau Bkp translate into a set of bilinear algebraic relations for the coefficients, because these are all independent functions. It provides a basis. And so you can write down the evaluation of that formal residue in terms of the pi lambdas as bilinear expressions, and similarly for the kappa. And these are not arbitrary. These are very clearly understood geometrical relations that are familiar to everyone who is familiar with Grassmannians. The partitions, at least partitions that fit into a given rectangle, are the so-called Plicker the pi lambdas are the Plicker coordinates of an element of a Grassmannian. But this is an infinite Grassmannian, so there's no rectangle limiting the size of lambda. The Young diagram can be as big as you like. It's actually an infinite Grassmannian. So associated to every Kp tau function is an element of an infinite dimensional Grassmannian, and these are the Plicker coordinates. I'll get to exactly what that is in a moment, but these are the Plicker coordinates, and they famously satisfy these bilinear Plicker relations. What is meant by this is that you take an arbitrary pair of partitions lambda mu, and you remove one element, lambda I, from one of these and add it with a shift to the other one, put in a sign and sum, and that identically always gives 0, and those are the Plicker relations. What they have a geometrical meaning. They give you the image of the Plicker under the Plicker map, which realize the Grassmannian as a projective variety. It's an embedding. The Plicker map is an embedding into, in this case, an infinite projective space. And that projective space is what physicists would call the fermionic Fock space. It's an semi-infinite exterior product space, projectivized. Similarly, and the pi's themselves are determinants. They're determinants of submatrices of the matrix of homogeneous coordinates of the elements of the Grassmannian. Similarly, for the BKP, the kappas are not determinants. They're Pfaffians of a skew matrix, and they are very similarly. There's a map due to Cartan, which can be found in his book on spinors, which embeds not general Grassmannians, but the so-called maximal isotropic Grassmannians with respect to a quadratic form into, again, projectivized exterior space, which, again, Fermi-Fock space. Well, it's finite dimensional for Cartan, but for our purposes, it could be infinite dimensional. It is infinite dimensional. And these coefficients, which play a role very similar to the Plicker coefficients, I like to call them the Cartan coefficients because he's the one who introduced them. And the Cartan map is based on the Clifford algebra. Basically, it's the theory of irreducible Clifford modules. And what's very important is for physicists who happen to be in the audience, these maximal isotropic Grassmannians are exactly the same thing as projectivized pure spinors. And pure spinors are playing a big role and have played a big role in physics. But that's Cartan's theory, the fact that projectivized spinors in general are associated with isotropic subspaces of a vector space with respect to a quadratic form is Cartan's construction for spinor modules, and the smallest orbit under the spin group within the spinor module or the Clifford module is the pure spinor orbit. Okay, so now I'd like to introduce a little bit of matrix notation. Underneath this is lots and lots of matrices, and I'd like to state a result. The result is really just an identity between determinants of a skew, of submatrices of a skew matrix. Maybe I'll even write it first. Maybe I'll show you the identity I'm leading up to. Where is it? Here, no, here it is, right. This is the identity. So we're going to have a skew matrix of which we take minors with columns I. So it's an n by n matrix. I is a, let's say, R element subset of the numbers 1 to n. J is an R element subset. And this is the minor whose columns and rows are given by the set of integers I and j. You take the determinant of this, then the theorem which I'm leading up to, just as an identity which expresses this minor determinant, which could be off diagonal, it's not necessarily a principal minor, as a finite sum of principal minors, but not determinants of those. So you form the diagonal submatrices with rows and columns K and rows and columns L for pairs KL of subsets of 1 to n. And these are skew because they're along the diagonal. And so you can take their Pfaffians and you form this bilinear expression in the Pfaffians, put in a sign suitably, and sum it up. How you can choose the K and L's, I'll explain in a moment. But basically, this is the formula I'm leading up to, which is nothing more than a certain determinantal Pfaffian identity. But it has deep meaning. It's not just a matrix algebra identity. It really has to do with relating the Plicker embedding and the Cartan embedding. This tells the relationship between the two. Okay, so let me just go back to a little bit of formalism. So we have our skew matrix A, n by n. We have the minors with columns I and j, which has rank, which has dimension size r. So it's an r by r matrix. And we define something which we'll call a polarization. So every pair ij of cardinality r, and we're ordering it now for convention's sake in strictly decreasing order. So that is really a strict partition. However, its values, the values of its parts are only between 1 and n. There's no 0 there, but you'll see in a moment that there's an associated sequence with possible zeros. Okay, so you take a pair ij, and a polarization of that pair ij is another pair, KL, with not necessarily cardinalities r and r. However, the cardinality k, little k, and little l, they add up to twice r. So the total cardinality is the same, but this could be smaller and this larger, or vice versa. And the property for polarization is that the union of k and l must coincide with the union of I and j. And the intersection must coincide with the intersection of I and j. We'll call that S. Now, the fact that the union here is equal to the whole set of 1 up to n is just for simplicity's sake. If the matrix happened to be bigger than the cardinality of the union, we would just look at the part of the matrix, just the principal minor, which corresponded to the rows and columns I union j. So we just take a square submatrix. So for simplicity, we may as well take it as the whole thing. But this constraint that it should equal the whole sequence of 1 to n is not necessary. It's just that the other matrix elements don't enter into the identity. So we may as well assume that the union is n. Okay, so we've got the notation now for polarization. Now I have to add something. Okay, it's a simple combinatorial fact that that the number of distinct polarizations, first of all, k plus l is equal to 2r, and the number of distinct polarizations is purely combinatorics. It's binary arithmetic, is 2 to the 2r minus 2s. Now, we want to add some data which makes each polarization a permutation under the symmetric group in 2n elements, in t elements, let's see. Yeah, in n elements. So we want to add, no, sorry, the number of elements is 2r. So we want to add some data, which even if there are overlaps, as there are, between I and j, so even if the intersection of I and j is non-empty, S is non-empty, makes a distinction between those which belong to I and those which belong to j, or those which belong to k and those which belong to l. So what we do is we add a binary number to each. So either a sign, let's say a sign, or 0, 1. We add a binary sequence. So we make it into a sequence of pairs. So we have 2r integers, of which there may be repetitions if the intersection of the two sets is non-zero, and we add a sign to each of these. Now, if we have a pair k and l, we're going to define what is meant by the sign of k and l. So there's a unique, this is actually a little lemma, there's a unique binary marking of the sequence I1 to IR, J1 to JR, such that when the two elements, this sequence of elements coincide, if one from here, if there's an I equal to a J, then by definition, we assign the plus sign to the first and the minus sign to the second. That's fixed. The remaining ones, which do not belong to the intersection, we assign in the unique way, there's only one way, that makes the particular sequence K plus L minus, which means K, the K1s, KK, are all assigned to plus, and all the L's are assigned to minus, which makes this sequence into a permutation of this. So once you fix this rule, the first rule of coincidence, there's only one permutation, only one sequence of epsilons for which this is a permutation of this. So I hope you understand that the IJ is essentially containing the same set of elements, but with more or less intersections, and the way that they're divided between the I and J is different from the way they're divided between the K and L. And so we're adding some data in order to uniquely determine what, for a particular polarization, what the sign of that is. And the statement is that we define it to be the sign of this permutation, the permutation which takes you from this marked sequence to this marked sequence. Is that clear? This is just a definition. It's not really complicated, but it's a little bit technical. Maybe I should stop and ask, are there any questions? Okay, so I'm going to continue. So we know now the definition of the sign of a polarization, a little more notation, because this is all about signs. The cardinality of the intersection of I and K we'll call pi of K. And the intersection, the cardinality of I intersect L we'll call pi of L. It's very easy to see that the sum of these two must equal the cardinality of I and J plus the cardinality of the intersection. So I already defined the notation. Aij is the R by R minor with rows I and columns J, and KKLL are the principal minors with rows and columns K, rows and columns L. And I've already shown you this, this identity. So I'm just telling you that this is true. It's not a trivial thing to do, but one can actually deduce it from the considerations of Cartan and his Cartan map into an exterior space of an isotropic Grassmannian. That's an isotropic Grassmannian has affine coordinates that are skew symmetric, and that's what these A's are. And when you take their Pfaffian, those are the Cartan coefficients that I was speaking about earlier. And when you take the square of a Pfaffian, you get the determinant, but there are determinants well defined for the off-diagonal blocks, Ij as well. And this relates the two. And basically what this is doing is giving the Plicker coordinate. You're taking a Grassmannian consisting of n-dimensional subspaces of a 2n-dimensional quadratic, two-dimensional vector space with a quadratic form that is canonically defined, as Cartan does. And we're looking at all the Plicker coordinates. That's really what these are, all the Plicker coordinates. And we're equating them to bilinear sums over a finite number of Cartan coordinates for an maximal isotropic Grassmannian in which all the inner products of the basis elements vanish. So the secret meaning of this is really geometrical. It's the relation between the Cartan map and the Plicker map. Okay. Now this is just the matrix identity, but now I want to give I'm going to give a very great generalization of this, which is actually the same thing where the A's are interpreted in specific ways. So all we need in general is skew symmetric matrices. Well, there's a way to get that. In particular, using Schur functions. So remember the notation, or in fact for this notation I didn't introduce before. If we introduce the restriction of the KP flow variables, to those where the even ones are equal to 0, that is equivalent to giving the parameters for a BKP flow variable. And I already introduced this notation, the Frobenius notation for a partition. Then this identity, which is purely a matrix identity, but it does relate a determinant to a sum of products of Pfaffians. And remember, the Schur function was defined as a determinant, and the Schur function was defined as Pfaffians. So in fact, in a sense, a special case of this, suitably interpreted, is this relation between Schur functions and Q-Schur functions. Now, this relation, in fact, was not known until a year ago, except for special cases. If you look at McDonald's book, which includes detailed discussion of symmetric functions, 2 special cases of this general formula can be found. One is when, I'll show you in a moment. One is when beta is essentially the same as alpha, and that's very simple. Then you have only one term on the right-hand side because there's only one polarization. And the other is when both alpha and beta have cardinality 1, and that is what's called a hook partition because there's only one arm and one leg. So just to introduce the notation, we're reminding you of the notation, the cardinality of the intersection of alpha. And so I'm going to write, this is also a sum over polarizations of the pair alpha beta. These are polarizations of alpha beta, which I'm calling mu plus and mu minus. So it's the same sort of relation, slightly different notation. So it plays the same role as the K, L, and IJ. The alpha and beta have the same cardinality, and the mu plus and mu minus do not have the same cardinality, but the sum of their cardinalities is twice that of alpha and beta. And so this is the same notation we had before. We call the cardinality of the, mu hat is the same as mu if mu is even, or as I said, it's mu together with 0 part if it happens to be to have an odd number of elements, because we need an even number of elements to take Pfaffians. There's a slight kink relative to this, and that is here we just had values I and j between 1 and n. And here the alphas and betas can take values between 0 and n minus 1. So there's a slight shift. But if you add 1 to each of these, then it's between 1 and n. And what's called a, this is just a purely technical point, that what you really are polarizing is not alpha beta, but alpha and the shift of beta by 1. So I don't think I have to dwell on that. And M is the cardinality of this extended strict partition. Okay, so here are some examples of that general formula. The general formula expresses an arbitrary Schur function with any partition whatsoever, evaluated at this special value where the even flow parameters are 0, in terms of a bilinear sum over the Q Schur functions, where the strict partitions labeling these Q Schur functions are all polarizations of the pair alpha and beta. And the signs are picked as I said, you choose the sign of this polarization, and there's another sign which adjusts according to the cardinality of mu and so on. So 2 specific cases of this can be found in McDonald's book. One is when the partition in question happens to be a so-called double. So a double is determined by the first half of the Frobenius indices, alpha, and the second half is the same thing shifted down by 1. Obviously, it only makes sense if this is greater than or equal to 1. So that's called a double. So the double of a strict partition alpha, the alpha is an ordinary partition with Frobenius indices alpha and alpha minus 1. Now, it's very easy to see that there's only one polarization of a double, and it's itself, essentially. So alpha alpha is the only polarization that's allowed. Notice we added 1 on this to the second one to get equal alphas. And in that case, this identity, which I've written down in general here, is double star, turns into this relation, which is in McDonald's book. It says that the Schur function for a double, for a partition which is a double, up to this normalization factor, is the square of the Q Schur function for alpha, evaluated at 1/2 of the flow variables, and these are only the odd flow variables, the TB, or only T1, T3, et cetera, et cetera. Similarly, if R is odd. So this can be found as an exercise or actually as an example in Ronald's book. A second example that I will list is when we have a hook partition. So a hook partition is one which has only one diagonal. So the Frobenius rank is 1. So it's a pair of non-negative integers. And assuming these are distinct, there are 4 polarizations, either A and B plus 1, or B plus 1 and A, or the null set and A, B plus 1, or A, B plus 1 and the null set. Those are the 4 distinct polarizations, but they pairwise, they contribute twice the same factor to this sum. So in fact, there are only 2 terms of the sum, and this is the sum. So the relation, and this also can be found in McDonald. For a hook partition, the Schur function evaluated at T prime is this bilinear combination of Q Schur functions. Okay, so all of that is a run-up, a preliminary to the main result that I'm going to present, and I think I only have about another 5 or 10 minutes, so I'm going to accelerate a little bit. I have to give a way to construct all tau functions using fermionic creation and annihilation operators. So this is really the infinite dimensional analog of the irreducible Clifford module that Cartan defined. We take now an infinite dimensional space, let's say a separable Hilbert space, which we'll call H, with bases labeled by the integers, and its dual, H star, so with the dual basis. Then for the semi-infinite, what we mean by the semi-infinite wedge product is all linear combinations of wedge products of the basis elements starting on the left and going infinitely to the right in such a way that all of these indices are strictly decreasing and are given by this formula in terms of a partition. So the formula is the indices are lambda j is the part lambda j minus j plus an integer n, which is called the fermionic charge. I won't explain why it's called that, but it's called the fermionic charge. And these are the basis elements which span the entire fermionic Fock space F, which is the semi-infinite wedge product space. So notice that whereas lambda is weakly decreasing, L's are strictly decreasing, and eventually they saturate in all successive negative integers, because these saturate in zeros, these saturate in all successive integers. Okay, now we have the fermionic representation, which is, again, due to Cartan. The exterior product is denoted psi j, acting on that wedge product space. And the interior product of the dual element is denoted psi j bar, and that generates the Clifford algebra of anti-commutators, corresponding to a quadratic form in which the space spanned by, well, the space H is totally null, the space H star is totally null, but the scalar product of an element of H and of H star is exactly the action of H star on H. So it's a canonical quadratic form, and that's what is defined by Cartan in finite dimensions. An alternative way to represent the basis elements is using the Frobenius indices. If you take the Frobenius indices of the partition lambda and pair them so that you take, if you're in the nth, now I didn't mention this, but everything here is referred to a vacuum vector. So for each integer, there's a charge n vacuum in which essentially you have, well, L1 is n minus 1, L2 is n minus 2, et cetera, et cetera. That's a that is the vacuum vector, and everything can be built out of that vacuum vector by adding creation operators and annihilation operators. So if you take the nth charged vacuum and apply this product of pairs of creation and annihilation operators determined by the Frobenius indices alpha j and the negative of minus beta j shifted by n, you get, it's an easy calculation, you get back the basis element I defined before. And here's the fermionic representation of the Kp tau function. It is the vacuum expectation value of the product of three types of terms. They're all elements of the Clifford algebra, all representations of the Clifford algebra, so they're all fermionic operators. This is a group element, which is represented by exponentiating an algebra element, which is bilinear, the psi, m psi, dagger. This is standard. The gamma plus is the flow group, which actually determines the abelian, the commutative flows. And U could be absent or could be present, but it's a polynomial factor. And the main thing about the polynomial factor is that not everything is exponential. You might have to add in terms acting on the vacuum, which don't just contain exponential factors, but also polynomial factors. I won't go into the details. So the polynomial factor looks like this. It's a product of creation and annihilation operators where the U's are linear in the psi's, the V's are linear in the psi's, so the V daggers are linear psi daggers. And any product of this kind is a Kp tau function, and vice versa. In some sense, every Kp tau function is and you just suppress the group element, put in the identity element there, and choose for your homogeneous algebra element, the monomial, choose exactly this sequence of products of Fermi creation and annihilation operators corresponding to the Frobenius indices. So that is a tau function. And a direct calculation using Wick's theorem tells us that this is a determinant, and which determinant is it? Exactly what gives the Schur function with alpha beta as the Frobenius indices. So that's the fermionic representation of Schur functions. Now I think I have to accelerate because time is passing. To do the same thing for the Q Schur functions, we introduce so-called neutral fermions, which are relevant for Bkp Tau functions, which are these linear combinations of creation and annihilation operators with opposite signs of the indices. There are two classes of them, the plus kind and the minus kind, and it's very easy from the Clifford algebra relations to check that they anti-commute mutually, so they don't see each other. There's the plus kind and the minus kind. I'm worried a little bit about the time, so I'm going to just run through this a bit quickly, but we have a smaller subspace of the fermionic Fock space, which is spanned by, as a Verma module, by acting on the vacuum with the neutral Fermi operators of positive index. The negative ones annihilate the vacuum, the positive ones don't. And there are two kinds, the plus kind and the minus kind. These just give you two isomorphic copies of subspaces of the fermionic Fock space, which is actually the Fock space corresponding to a smaller a subspace of the original Hilbert space. Okay, here's what I failed to write down before, but what was implicit in the Clifford algebra Fermi anti-commutation relations. This is the quadratic form for which we're defining our Clifford algebra. And these are the two subspaces of the original Hilbert space that correspond to the neutral fermions. Okay, so very similarly, we define group elements as exponentials of bilinears. This generates an infinite orthogonal algebra. And this is an anti-symmetric matrix. So here's the fermionic representation of the infinite orthogonal group. And once again, the Bkp Tau function has a vacuum expectation value.
Question? Sorry. Could you go back to the previous screen?
Yeah.
Isn't this sign right? Yeah, quadratic form Q. Do you want this to be symmetric or just
this is symmetric.
Oh, okay. Okay.
Okay, so here is the general expression as vacuum expectation values of a Bkp Tau function. We again have an abelian flow group. Here only the odd elements enter. It's again bilinears in the neutral fermions that enter. Yeah, I think I left something. Yeah, this is correct. We take linear combinations of these so-called currents, which are bilinears in the field components, and exponentiate that. That gives you the abelian group. This is an abelian algebra formed from the bilinears, a subalgebra of the orthogonal algebra, and the corresponding group. The two don't see each other, they commute. And again, we could have products of plus or minus elements, which are linear combinations of the basis elements. Okay, so in particular, once, just like with the Schur function, if you set H equal to the identity element, and you choose for the U's exactly these fermionic basis elements, the neutral fermions, then you reconstruct the Q Schur function. So that's the fermionic representation, and that shows in particular it's the Bkp Tau function. Now, I think I'm not going to be able to give any proof, but I will now define a lattice of Kp and Bkp Tau functions and finish with the formula that relates them. So for each group element G, you see this is the lambda basis element, as I wrote before, is just the vacuum acted on by these bilinear pairs of creation and annihilation operators. So there's already a monomial in the creation and annihilation operators that is there. So this is a Kp Tau function. For each partition with Frobenius indices alpha beta, this is really a vacuum expectation value. If I replace lambda by the vacuum acted on by bilinear pairs. So this is a Kp Tau function. It's a lattice of Kp Tau functions labeled by partitions. And very similarly, I can define a lattice, I'll call it kappa alpha H of Tb, which is determined by a group element in the infinite orthogonal group. Again, this is just the vacuum acted upon by a sequence, a finite sequence of neutral fermion operators. It doesn't matter if you choose plus or minus, it gives the same function because it's the same algebra. And so these are Bkp Tau functions labeled by strict partitions. In the particular case where the H is absent, we recover the Q Schur function. And in particular, if you take G, the infinite group element, as the product of a plus representation of H and a minus representation of the same group element, then it's very easy to see that the Kp Tau function corresponding to G is the square of the Bkp Tau function corresponding to H. Okay, I have to accelerate a little bit. So again, this is just a repetition of the definition of polarizations. I'm not going to repeat that, but I said to you that I would give you a much more general form of that determinantal Pfaffian identity, and here it is. Now, instead of having an arbitrary determinant here, we have the determinant which defines a Kp Tau function. It's an infinite determinant. And instead of the arbitrary Pfaffians of minors, of principal minors, we have the the Bkp Tau functions that I just defined before. And this identity is a realization of that determinantal Pfaffian identity in which the matrix is an infinite matrix defined essentially by the affine coordinates of the Kp Tau function and the Bkp Tau. Actually, it's the Bkp Tau function that gives the skew symmetry, but this is a doubled expression. G of H again is H plus and H minus. So H determines everything, and this is the most general form of that determinantal identity expressed in terms of Kp and Bkp tau functions. So I think I've run out of time. I apologize for that. I had another remaining part which gave polynomial representations, I mean, explicit determinant Pfaffian polynomials for these types of tau functions. But when a condition is satisfied on the group element, I don't have time for that. So I'm going to just end with the display of, I can't, unfortunately, the proof is, there's no time for the proof. So the proof is based on a factorization lemma, which is also based on the fact that the two types of neutral fermions mutually anti-commute, which means that when you have a vacuum expectation value of a product of two types of fermionic operators, they factor. So that everything goes down to that, but I can't go into the details. So this is the main result of the seminar, and this has multitudinous applications in both matrix algebra and special functions. You can realize this depending on which type of tau function. You remember we have a huge variety of tau functions. If we are putting in Q-Schur functions, we get the Schur function. We could put in rational solutions of any kind. We could put in elliptic or hyperelliptic or any kind of theta function solution. Every case of such Kp tau function gives you back the Bkp tau function gives you back Kp tau function. So this gives a multitude of special function identities on every version of tau functions you can think of. Okay, I think I'll stop there. Thank you very much.
Thank you, John, for this very interesting talk. And now we have time for questions. So please, if you have any questions.
Yeah, could you go back to the definition of a Kp tau function and Bkp tau functions?
Okay. This is the Hirota relation defining Kp tau functions. And this is the Hirota relation defining Bkp tau.
So what's the what's the main characteristic of these definitions? So somehow you are
this definition is this. Remember, we're talking about infinite Grassmannians. I didn't really fill in all the details, but what this is saying in infinite dimensional Grassmannian, it is exactly the so-called Cartan relations for an element of an infinite maximal isotropic, quadratic isotropic Grassmannian. So it contains in it, because it's infinite, every possible Cartan relation for all possible Grassmannians. So I'll just recall what those are. Here are the Cartan relations for the Cartan coefficients, defining the embedding of an isotropic Grassmannian into an exterior product space. And these are the Plicker relations, defining the embedding of a or the image of the embedding, Plicker embedding of a Grassmannian in an exterior space. So in fact, this is a way to encode the infinite set of Plicker relations, and the other one, this is the infinite set of Plicker relations, and this is the infinite set of Cartan relations. Every tau function is determined by an element of an infinite Grassmannian.
So when you say that this is maximally isotropic Grassmannians,
yes.
That if the quadratic form is symplectic, that means it's a Lagrangian subspace, right?
Lagrangian is another category. There is such a thing. It's called a CKP tau function, but I'm not talking about that today. But there is, you're right, there does exist for Lagrangian Grassmannians, there does exist a hierarchy, which is called the CKP hierarchy. For some strange reason, which I cannot quite explain, it is not defined on an as vacuum matrix elements in a fermionic Fock space, but in a bosonic Fock space. But that's a completely different topic.
Okay, thank you.
Okay, more questions? So actually, I have a question about the main result. So the question which I guess physicists should ask. So you have a very universal formula relating tau functions of Kp and Bkp. But do you have in mind any particular application of this formula? So I understand that the formula is universal, but do you know any example when this formula can tell us? So you mentioned many different families of tau functions coming, for example, from geometry.
Yeah.
Do you know if this formula can tell us
this is the general
something?
formula.
Yes.
Now, we just saw two examples. One was simply an identity of about minor determinants of a skew matrix. This is just that is a special case. I should have said that. If you set the t flow parameters all equal to 0, and look at the g and the h, just determining a skew symmetric matrix. Well, H actually determines a skew symmetric matrix because you apply H to the vacuum, you get an element of the isotropic Grassmannian, you write down as affine coordinates, and that's a skew matrix. So in fact, that gives you back this. There's no time involved. There's no flow variables involved. It's just a matrix identity. So that's one application. The other application, of course, was the generalized relation. This was not known actually, but this generalized relation between Schur functions and Q-Schur functions, which I wrote down before. This is also can be viewed as a special case of that general formula. Now, I challenge, I mean, I give this as a suggestion to possible students who are looking for research problems. This is completely general. The H could be anything. By picking different values of H, you get identities between completely different types of special functions. They're all tau functions. So, for example, well, the Schur function is a special case, and for that, well, the H is chosen in such, well, okay, there's a special choice of H which gives you the Schur function. Suppose you didn't choose. So Schur functions are polynomials in the flow variables. Suppose you didn't choose a Schur function. Suppose you chose H to give you a BKP solitone. So you have BKP solitones. Those are exponential type solutions. So if you choose BKP solitones, there's an associated G of H, and that gives you some special kind of Kp solitones. So this is a relation, bilinear relation between Bkp solitones and Kp solitones. That's another application, which is the detailed formulas have yet to be written down, but these objects can be explicitly written down as ratios of sums of exponential functions. That's another application. Now, Sasha, for you, what would be interesting would be to take the case of matrix integrals, because you're specialized in that. You know the hypergeometric and the various types of tau functions of various kinds. Some of them are of great interest as generating functions, and there should be some relation. For instance, when kappas become, you choose H, for instance, to give a BKP tau function, let's say of the type you studied. So let's say the BGW tau function. Choose H appropriately. What is G of H? What is the relation between these? What is the resulting? Could it be that some linear combination? Remember, these are also labeled by partitions. So these are not the actual original tau functions, which would correspond to the trivial partition, but there's a whole lattice of them. So first of all, for each group value, there's not only the original Bkp tau function, but the entire lattice, Schur lattice of them. How are they related? For instance, if you pick some familiar Bkp tau function, what is that lattice? Those are also solutions. Maybe it has some applications. It may be something related to Darboux transformations acting on the original one. So exactly what you put in here is your choice. Every time you pick a new H, you'll get a new class of identities.
Thank you. Thank you. So I'm afraid we have no time for more questions. So let me thank the speaker again. Thank you, John, very much for this very interesting talk. Thank you.
It's a pleasure. Thank you very much for the invitation.